All right, team, welcome back. In the last lesson, we built the mathematical machinery for the cost function. But formulas alone don't give anyone intuition. So today, we will put the math aside for a moment and walk through a simple visual example to understand what the cost function means and how it guides us to the best model. This is one of the most important concepts in machine learning. If you get this, every ML model you build will start making a whole lot more sense. Let's consider a very simple training set. Imagine I give you 3 tiny data points, super clean and simple. If you plotted them on a graph, you would see they fall perfectly in a line. Now, let us use a simplified model of f of x equals w dot x plus b for our test, and let's assume b equals 0. No b for now. We will bring the bias term back later. Our model produces estimates for every training example. Remember, I corresponds to each training example and ranges between 1 and m. In our case, m is 3 since we only have 3 training examples. So every choice of w gives us a different straight line. And the cost function measures how off our predictions are. Okay, let's not stare at the formula too long. Instead, let's see what happens when we try different values of w. We're going to test 4 different values of w and see what the cost function looks like for each one. Basically, we will compare how good or bad each choice is, and we will see how the cost changes as we tweak w. We're going to test 4 values of w: 1.2, 1.8, 2.0, and 2.5 to compare how each one affects our model. All right, let's kick off by testing our model with our first value. Let's see how well the line fits with this choice. We can see that in this case, the cost is relatively large at 1.493, since the squared error is relatively large at 8.87. In this case, our model is underestimating, and our red line appears below our training data points. Let's now change the value of w to 1.8. In this case, the cost is relatively small at 0.093, and our model is making better estimations, but still a bit underestimating. We can see that the model's red line still appears below our training data points, but not as much as in case 1. For case 3, we're bumping w up to 2.0. This is perfect. Cost is 0 and model is perfectly estimating, with our model line perfectly aligned with training data. Now, let's crank w up to 2.5 and see what happens. We can see that in this case, cost is 0.583, and this time our model is overshooting, and model's red line appears above our training data points. Now, let's see how the cost curve looks like. Let us plot all 4 cost values on a separate graph. This creates a U-shaped curve with a minimum at w equals 2.0. All right, now let's take a look at a very interesting 3D visualization. This surface shows how the cost function changes for different values of w and b. Every point on this surface represents a possible combination of w and b, and the height of the surface tells us how big the error is. The higher the point, the worse the model performs. The lower the point, the better. Notice that x near the bottom, that's the local minimum. This is the spot where the cost is the smallest, meaning the model fits the data best for that particular w and b. One great way to visualize this is to imagine this 3D plot as a mountain landscape with a single lowest value at local minimum. Now, on the right, we are slicing that 3D surface into a 2D curve by fixing b to 0 and only looking at how the cost changes with w. This gives us the classic U-shaped curve for cost. And again, that red point labeled local minimum shows the value of W that gives us the lowest cost with B equals 0. That's exactly what algorithms like gradient descent are trying to find. Okay, let's recap our takeaways from this lesson now. Every value of W produces a different line. Each of those lines gives a different cost. The cost function is a searchlight that guides us to find the best model. The best value of W is where cost is the smallest. For our data set, that was W equal to 2.0. The 3D plot showed us all possible combinations of W and B. Our goal is to find the lowest point, or the local minimum, because that's where our model performs best. And finally, local minimum is exactly what algorithms like gradient descent are trying to find. And that's the intuition behind the cost function. Not just math, but a way to measure how good our guesses are so we know which direction to move in. Next up, we're diving into a super cool idea called gradient descent. Think of it like a hiking guide that helps us find the lowest point in a valley. Instead of wandering around blindly, this algorithm guides us all the way down to that sweet spot called the local minimum. It basically works like a GPS for us for getting to the bottom. Let's go there next.